process of metamorphosis, which is how butterflies form from larvae to pupa and adults and all of that. The butterfly needs to transform. The simple answer is because it needs to be able to fly, right? When it was an egg, well, it did the things that eggs could do, but it couldn't do the things that larvae could do. And so at that point, at the right time and at the right place, well, it had to transform to carry out the functions that were needed of it at that point in time. And of course, when it needed to fly, it had to develop wings. In a very simple nutshell, that explains why transformations occur. It's simply because we need to be able to do a particular function at that time, and we have the potential, but we can't perform the action at that point yet. Of course, the larva has the potential of flying, but it cannot fly. The potential does not equal actual execution, right? So for those two things to happen, then the larva needs to be able to transform into a form that can execute that action. And that's why transformations are needed. So we can generalize as follows, that when you have potential and you need that potential to translate into actual outcomes, well, you need to transform. Look at this, illustration here. You have a child who is on the road hawking goods or selling things. That child has potential to be a doctor. But for that to happen, that child has to be transformed, right? That's why they go to class, and then they learn, and then they achieve that potential. And so herein, we make a discrimination between potential, right, versus actually attaining the status. It's the exact same thing that happens in statistics, right? You might have a certain variable that has the potential to be used for something. But the fact that it has potential doesn't mean that it can be used. Maybe because there are some aberrations that exist at that moment that prevent it from being used. And so we apply a process of transformation so that then it can be used for that particular purpose we have in mind. So like I said, we will be looking at transformation from the broadest possible angle. Essentially, it could involve transformations that occur at the level of the data set, in which case we're looking at processes or actions that change the dimensions of data. By dimensions, we mean the number of rows and the number of columns. So here you can immediately think of processes like append or merge. We'll discuss some of this further. But again, we're thinking from the very highest level possible, the broadest angle possible, that transformations could occur at the level of the entire data set, or it could occur at the level of some data sets, some variables, not the entire data set, or it could be limited to just a single column or variable in our data sets. So processes that occur at the level of the entire data set could be things like append or merge, or reshape of the data set, where we switch it from long to wide formats. And then you could also have processes that impact some variables or some columns, but not all of them. So, for example, we might have a bunch of variables, and we're trying to summarize all of those variables into one single column, right? In a way, we're transforming the data to make it easier for interpretation. We'll look at some examples as we proceed. And then the traditional context of transformation, when we say transformation in statistics, the first thing that jumps to people's minds is numeric transformations, things like log transformation. So when you just say the word transformation, the first thing people think generally is, oh, power transformations or square root transformations or log transformations. Obviously, those are also very valid forms of transformations, which we can put under an umbrella of numeric transformations. Numeric because you can only do those actions on numeric variables, which is variables that are numbers 1, 2, 3, 4. You can't do those on variables, for example, that are string. But a very important form of transformation that we also need to talk about is handling of missing values. We started a discussion yesterday about missing values, but it's very important to also discuss that as a form of transformation, because obviously it automatically changes the behavior of a variable. Whether you impute missing values or you apply inverse proportionality weighting, obviously changes the entire behavior of that variable. So it is a form of transformation of that variable. So we're going to discuss that to see how that impacts the validity of our findings. All right, let's get started into the processes that affect all of the variables. So the entire data set as a whole. So here we'll talk about two things, merging and appending. A merge is when we take two or more data sets and stick them together so that we have a wider data set, right? Obviously, it will still be a bit longer, but in general, with merge, we're focusing on data sets where we have data A and data B from the same individuals, and we have to link them together, right? So that is what a merge refers to. So here, for example, we have dataset A that contains information for person A and person B. So dataset A has information for variable 1. Dataset B has information for variable 2. You can see here that both dataset 1 and dataset 2 contain the same individuals, A and B, right? So a merge will say we would link them together or we will merge them by the unique ID. So it's like sticking them together side by side so that we have a new data set that still has information for persons A and B, but now instead of just one column, we have two, variables 1 and variables 2. So that's what we mean by merge. Append is different. Append means that we're taking a data set and stacking them one on top of the other. So append will generally result in a taller data set that is, higher. So we take, in this case, we have data for persons A and B in data set 1, and for persons C and D in data set 2. So append will say, let's take them together and let us stack them on top of each other so that now we have a data set. It's still the same variable that is still here, but persons A, B, C, and D. Right? That's the difference. Now let's look at a real-life scenario to see in what cases we might need to merge or to append data accordingly. Let's look at the case study for NHANES. NHANES is the world's most sophisticated surveillance system. It's the gold standard for how surveys should be done. NHANES stands for the National Health and Nutrition Examination Survey. NHANES has data collection in three modules. You have the interview or self-reported components, where we'll give you a questionnaire and say, please fill this questionnaire. Then secondly, you have lab. So you can see lab data. You might have blood samples collected or urine samples or saliva samples, and they're sent to the lab for a whole bunch of things. And then lastly, you have exam data, right? So you have, these are the key elements, right? And so now for each particular data set you have, let's say the demographics data, if I look at the documentation here, this is the file and this is the documentation. These are the only variables that are in NHANES in the demographic file. I have the age and the gender and all of those things, right? And the weight, but that's all. There's nothing other there. So that means that if I wanted to do analysis of, let's say, smoking prevalence, and I want to see how prevalence differs among males and females, well, obviously, this file contains only demographics, right? So that means that if I want to analyze this data, I will have to merge the data set for the demographic file and the smoking file, right? So if we're to download this, let's look at the data file. So we already covered on day one the types of file. The XPT files here you have, for those of you who aren't there, just to give you a quick bridge to what we covered. So we'll talk about day one, we'll talk about different types of file formats. I said XPT is a SAS transport file. Its main job is just to transport the data from one format to the other. And so it's a machine readable data set. So when you open your data set and you see these kinds of things, don't think it's a virus. It's not, okay? It's just the format of the data. Anyway, back to topic. So here let's say we want to have data for the demographic file, and we also want to analyze data on smoking. So that will be under, let's say, examination data. Let's see. I think that would be questionnaire data. Let's see. Under questionnaire, you have different topics. So you see, even on that questionnaire, it's not just one huge data set. You have, because it's a very detailed survey. Imagine if Enhance didn't break it into small chunks. Oh, you'll have one file that will be this big. So that even if you wanted to just analyze smoking only, you'll still have to download this massive file that has thousands upon thousands of columns. That would be very inefficient from a user perspective. So that's why from an administrative perspective, we split the files into small chunks so that you don't have to load unnecessary variables that you don't need. That's the idea behind it. So here, I'm interested in smoking. So I'll look for the smoking file under self-reported information and smoking cigarette, right? So if I look at this documentation, these are all the questions here have to do with smoking. So that means that if I wanted to analyze the prevalence of smoking among adults, I'll have to download this file. But remember that this one doesn't have demographic information. So I'll have to save the file, the demographic file, and the smoking file, and then merge them together. All right, let me show you how we do that. So I've already downloaded them. So I'm just going to demonstrate how we can do that. And let's start a new project. Let's call this day 3. Data transformations. All right, so in this case, I'm interested in the demographic file, in merging results for the demographic file and another file, let's say smoking. So I'm going to click on upload and I will select my file. I already have it here. So that's the demographic file here. Again, for those of us who weren't here on day 1, we said that when you look at the letters after the last dot, it's called the extension of the file, and that tells you the kind of file it is. So in this case, this is XPT, which is a SAS transport file. This is .csv, which is a CSV file. The Kairos platform can import data from any kind of format. So you don't have to worry about, oh, geez, I don't understand what this format is. The platform will just read it directly. So let's say we have, that's the file we have, the demographic file. So the platform has imported it. So here you can see the variables that are here. We have 43 columns or variables. Columns are the same thing as variables. And there are 10,537 rows, right? So now we want to merge the data sets for demographics and for smoking. So to do that, we'll come to data processing. So remember, I have already downloaded my demographic file, which I just imported. And I also downloaded my smoking file, which is on my computer now. My goal is to take those two data sets and merge them together. All right, so I'm going to come to data processing, come to combine data sets. And when you click on combine, you see 2 options. The first option is to append, and it says different individuals, or to merge, which is the same individuals. In this case, it's the same individuals I'm trying to combine their data sets together. So I'll click on merge. And now I'll have to pull up the data set for the smoking. So I'm going to click on upload file and look for where I saved the smoking file. So this is the smoking file here, SMQ. So I'll click on that and import. Now, if I try to merge this, I'm going to get an error because obviously I have not selected the unique ID that is common to the individuals. Because the question is, how will the system know that this is the same individual in this file versus that file? Well, the system will know because of the existence of a unique ID in both files, right? So you click the unique ID here. This is why you have to read the documentation. The only way you know that this is the unique ID is that you read documentation. So I'm selecting the unique ID here and the unique ID here. And once I do that, I click on merge. So the idea is that the same individuals have the same unique ID in both files. And so by selecting the unique ID, I'm just telling the system, look for individual with unique ID, so and so, and merge them. It's like you went to a survey that had a similar framework as Enhance, and let's say they use your phone number as a unique ID. So in dataset A, you have unique ID, which has your phone number and that of other people. In dataset 2, you also have that same structure. So we're saying, look for individual whose phone number is 123 here, and the guy who's 123 there, and that means they're the same person, and then link their records together. You don't have to sort in other platforms when you are trying to merge. You have to first sort data and all of that. On the Kairos platform, obviously, those are just manual processes that can easily be automated. So once you select the datasets unique IDs, you just click on merge, and the system takes that information and merges it. So now remember we had 30-something columns then. You see the number of columns has increased to 81 because now we have information coming from the second data set as well as from the first one. And that's how you merge on the Kairos platform. It's that pretty straightforward. Now, for append, it's the exact same thing. If we wanted to append, we would simply come to data processing, come to combine data sets, and this time, instead of selecting merge, we're going to append. Let's say we want to append a data set like, let's say, this is the one we're using for our case study, right? In this case, there's no variable that is common between this particular data set and the ones we just processed. For you to append, the variable names there must be at least one variable that is common to both files. You can't say I'm going to put dataset 1 on top of dataset 2, but there's nothing in common between datasets 1 and 2. There must be some variable, at least one variable that is common to both of them. So if you select a dataset, for example, that has nothing in common, it won't work. It will result in a failure. So you see here, dataset 2 does not have any matching variables with the current dataset. That's because at least one variable must be present in both datasets. The same thing applies for merge. If you're merging dataset 1 and dataset 2, at least one unique ID must be in both datasets. Otherwise, it will result in a failure. But bottom line, that's how you merge. So let's now find a data set that has some, let me pick up, let's see, let me look for a file that has some variables. I'll just select this. So now I just selected the same file again and appended it on itself. So now you can see that the number of rows has doubled, right? Appending means we're going to take the file and stack it on top of the other. When you append, you have a new variable created called the append source chi-squares. This tells you which records were present in which file. So here, for example, you see that this append source chi-squares has 2 unique values because we just appended 2 data sets. This tells you that the first one came from the first data set and the second one came from the second data set. So it's in the order in which they were arranged. And so that allows you to be able to figure out which responses came from where. There's no limit to the number of files you can append. It all depends on the memory you have. You can, in theory, append an unlimited number of data sets. All right, so that's how you implement append and merge on the chi-squares platform. I will call this data transformation because you can see that it has an obvious impact on the dimensions of our data set. Our data set just changed its number of rows and its number of columns. It's no longer the same data set it was. It's been transformed into something else. And that's why whenever you append, you'll see, I dismissed it then, but this always comes up. Set weighted analysis. because the platform recognizes that this is now a new data set. So it's asking you, well, do you want to set this new data set to weighted so that the analysis in it are weighted? We're going to cover weighted analysis tomorrow. But bottom line, both append and merge are data set wide transformations that will affect the analysis in all respects, because they dramatically change the dimensions of the data set in both the number of rows and the number of columns. All right, let's look at some key things we want to consider when we append. We want to pay very careful attention when methodology has changed, when you're appending. If a survey, for example, changes methodology in ways that are non-trivial, for example, you have NYTS. NYTS in 2000 and I believe 19 or 2020 switched from being a paper and pencil questionnaire to being a web-based survey. Now, that's a very important change. It means that it will be challenging for you to be able to compare estimates before and after that, because it's like comparing apples and oranges. So whenever survey methodologies change, you want to be very, very careful with appending data sets to analyze, for example, for trends over time, because there have been major changes in the methodology. The variables may be the same, but the methodology has changed. So it's very important to note that. Also, when you're doing weighted analysis and you have a weight variable and you append the data sets together, we rescale the weight by dividing by the number of cycles. So in other words, here we have appended two data sets together. If we're doing weighted analysis, we will have to create a new weight variable and divide that new weight variable by 2. So in other words, we want to say data processing will come to numeric transformations that involve, so let's go to arithmetic operations instead. So data processing, arithmetic transformations, we want operations between a variable and a constant. We'll select our weight variable and we will divide it by 2 to create a new weight variable. And I'm going to explain why we do that in a minute. So I'm going to call this, for example, weight 2, right? So for every row, it's going to take its value of weight and divide it by 2. So simple, it's not nothing complicated here. Just divide the weight variable by the number of cycles you've appended together. And the question is, why are we doing that? Well, in a weight variable, in weighted analysis, if you have, let me make this big. So let's say this is our weight variable. And this is individual number 1, 2, 3. And their weight is 10, 10, 10, right? This is cycle 1, let's say for the year 2020. And you took this data set. So we have 2 cycles of this data set for year 2020 and year 2021. Now, in complex surveys, the sum of the weight gives you the total population size. So in this population, we have 30 people, right? So if you sum all the weights, you're going to get 30. But when we append the data sets together, like we took this, appended them, so now we have individuals 1 through 3 and individuals 4, 5, and 6. By appending them together and using the entire data set as a point estimate for point estimates. In other words, we are appending the data sets together to increase our sample size, right? Now, obviously, as you can see, the sum of the weights is no longer, the population size is no longer equal to 30 anymore. It's double that, right? Now, that's not correct, obviously, because if you were, for example, to calculate weighted population counts, let's go back to something like an MMWR. Let me show you an example of what I'm saying. So in estimates like this, in reports like this, we usually say in 2017, 19.6% of high school students, which is an estimated 2.95 million users, reported current use of any tobacco products. How are we getting this number, 2.95 million? The answer is simple. We're getting that number by taking all those individuals who said they're smokers. So let's say we have a variable called smoking status here. Smoking status. And individuals are either non-smokers or they are smokers. Okay, this is the total here. So the way we get that 2.95 million number is that we take the weights for the individuals who reported one and add them together. It's that simple, nothing complicated about it. So in our analysis, we'll now say, oh, 20 of the 20 individuals were smokers, right? That comes directly from the weight. Now, now see where there's problem. You're saying 20 individuals were smokers in the combined analysis, which is supposed to serve one point in time. But that's not true, right? Because you appended two cycles together. So when the rule of thumb is whenever you are appending data sets from a complex survey and you have an intention to generate population count, you must take the new weights and divide them by 2. So in other words, here we're going to create a new weight, weight 2, which will be equal to the old weight divided by 2, right? Such that the total sum of this will still be equal to 30. So even though we have appended data set to increase sample size, the effective weights still add up to the weight for this or the weight for this, right? We have not altered the interpretation of the weighted population count when being used in the context of point estimates. So that's why that's why the note here says, whenever we append data sets together from multiple years to use to generate point estimates, we must divide the original weight variable by the number of cycles. Now, if you're not planning on generating weighted counts, if you're not going to say 20 people were smokers or 1.5 million people were smokers, then this is not necessary. It's not necessary to scale the weight. But if you have an intention to do that, the weight must be scaled. So those are practical things that you must keep in mind when you are appending data sets, because those things obviously have real implications on the validity of the findings you generate. All right, let's move on to the next thing. Now let's look at some of the operations that involve some variables, but not all of them. So here we're looking at arithmetic operations that will include multiplying data across multiple variables, dividing, adding, or subtracting. It could involve taking a summary across many variables. So it's like we have 10 of us and we'll say, oh, who's going to represent us, right? So we're going to pick one person to represent all 10 of us. Maybe that's the person with the strongest person. If we're going to go to a battle and go and fight, obviously we want the strongest person to go and represent us. Or it could be the guy who's average, the median, or it could be anything, right? How do we summarize multiple variables? And then we'll also look at some operations that the sum if operations. You are trying to count the number of variables that meet a condition. They're not classic transformations per se, but they involve some change in the dimensions of the data set, and they're extremely useful, so we need to be aware of them. Now, when you're doing arithmetic operations, you have to worry about missing values, about missing data. And there are two ways you can proceed with that. You can have an all or none framework, which means that all data points must be available, else that row is set to missing. And the reason why you're doing that is to optimize validity. The second framework to use is all none. I mean, in other words, as far as we have information for one person or two people or whichever variables, we're going to use them. And that prioritizes precision. Let's look at an example here. Let's say you're trying to do an arithmetic operation that involves 3 variables. You are trying to calculate an estimate of, let's say, poly tobacco use. And we do that a lot in reports. So for example, in this report, we have a variable like use of 2 or more tobacco products, right? So in other words, we get this kind of variable by creating a tally of how many products each individual uses. So in the real world, this is how we're going to do it. We're going to take generate a tally with arithmetic operations. So here you have cigarettes coded as 0, 1. We have cigars coded as 0, 1, and we have shisha. So for each individual, we're just adding 1 plus 1 plus 1. So here, this guy uses all three products. This is 0, 0, 0, so this is 0. So the question is, how do we handle missing values in this kind of context? Well, it's very clear that if it's missing, 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 then it will always return missing. Now, under the all or none, you must have information for every single product or for every single variable in question. And remember, these are row-wise operations, right? So here we come to this guy who has information for this and this, but it's missing this. Under the all or none, we will set him to missing because he doesn't have all. And here too, we have a case where you have 1 and 1, but he's missing information for this third product. We also set him to missing. And remember, we said the reason why we implement all or none is to optimize validity. Now, let's take a refresher from yesterday. We talked about types of bias, and we mentioned misclassification bias. Misclassification means that people that are supposed to be in this group are classified as being in the other group. See how that could happen. If an individual says 0, 0, how do you know that the third variable is 0 or 1? You don't know. They could have said they don't smoke cigarettes, they don't smoke cigars, but you actually don't know whether they're a smoker of shisha or not. The temptation might be to say they are, well, I'm just going to put them at 0, right? But that creates a problem if they actually, use this product, but you just did not know. So putting 0 here means that you're assuming. That's an assumption, right? And once your assumptions start coming into analysis, that's dangerous. Now, the same thing here. Now, for individuals who report 1 and 1, it's obvious that they use tobacco products. So 1, 1, 1, if our goal was to create a measure of whether an individual uses tobacco products, we can always classify this guy as a tobacco user. But the problem does not come from the guys who report 1. The problem comes from the guys who report 0, 0, 0, because you never know whether the last thing they did not provide information for is still a 0 or a 1, right? So when we talk about misclassification, the problem is not so much about the misclassification. The question really is this misclassification differential or non-differential? In epidemiology, we love it when everybody's equally screwed. We love that, right? There's no problem. People are being screwed, but everybody's being screwed equally. That's great, right? We don't like it when some people are being screwed over, but others aren't, right? Because here you see clearly that the risk of misclassification is going to be higher among those who report 0, 0 and have missing, and much, much less. I mean, you've already reported that you're a tobacco user and a tobacco user. So at least based on this, you are a tobacco user. And that's the whole point of an all or none framework, to say, well, I don't know about the guys who answered 0, and these guys also have missing values, so I'm just going to implement missing values to all. But the all none says, well, let's just use the information for the ones we have. So here, 0, 0 and 0 becomes 0 for some, and 1 and 1 becomes 2 for here. Now let's see how we can apply this in actual practice. In this case study, we're trying to implement the case definition for gum disease, which, by the way, is one of the most complicated case definitions that I know. This is an extremely complicated case definition to implement. It involves about 336 variables to implement this case definition of classifying individuals as having mild, moderate, or severe periodontitis, right? And this is how it works. In Enhance, for every individual, they do a full oral exam, and on each tooth, they take measurements on 6 spots around the tooth, right? So you have 1, 2, 3, or 1, 2, 3, 4, 1, 2, 3, okay, 4, 5, 6, right? 6 measurements around each tooth. They're checking for if they have a hole in their gum, right? And so at each of those spots, they're going to take a measurement. But obviously, we want to have a summary measure for this entire tooth that says, well, in summary, while we have 6 measurements, this one number represents the health of this tooth. So in this case, the question is, what should we take? Should we take the average of all the 6 sites? Should we take the worst case? Should we take the best case? Those are decisions that you as an analyst have to make. Now, obviously, if you have a case definition already, you don't have to make those definitions, right? But those kinds of decisions are decisions that you will have to make. As an analyst, you will have to summarize data at some point. You'll have to make decisions that say, well, we have 6 measurements on each tooth, but we're not interested in 6. We're not interested in sites. We're interested in the individual tooth. How bad is it? So how am I going to summarize this information about this tooth, right? Those are decisions you're going to have to make. And so you'll have to worry about, should we take the worst of the worst? In public health in general, we're always interested in the worst outcomes. So in general, most of the times we take the worst site as representative of that entire tooth. So we're going to see how we can implement this in just a minute. And so this is why it's complicated. You have 6 sites per tooth. You have 28 teeth per person, right? Because we exclude the third molars, the wisdom teeth are not included. And on each tooth, for each site, you have 2 different types of measurements. So it gets complicated. That's why you end up with 336 variables that have to be analyzed. Now, how has this been done traditionally? Well, for most researchers, analyzing ENHANCE is always a nightmare. This is one of the most feared data sets in public health because it gets really, really complicated really fast. So you see in this paper here, they said data were uploaded via SAS and handled with Microsoft Office Excel. For each periodontal case definition, specific Microsoft Office Excel data sets were derived to formulate appropriate algorithms. What they're saying in a simple case is that they have to now take the data sets and create a separate data set for each tooth. So now you have like dozens upon dozens of small data sets being created. And in general, as an analyst, whenever you are working and you start doing things that manually, that's not a good thing, right? Because any manual operation dramatically increases the risk for error, which is something you really, really want to eliminate where you can, right? And those are some of the reasons why chi-square was created, to say, how do we take these extremely complex operations and make them so simple that anyone can do them? So let's see how we can implement that kind of operation on the platform. You have 28 teeth, you have 6 sites on a tooth, and you want to, for example, generate a summary that indicates either the worst or the best, or whatever the case might be. So let's see how that works. So first of all, let's go to ENHANCE and let's see what we are referring to so that we have some context. Again, never ever start any procedure without referring to the documentation. That should be the single source of truth, right? So we're doing this to also reinforce good behavior by just going back to documentation every single time. So here we go to the examination data and we come to oral health. So oral health, you have oral health dentition, which measures the teeth. But we also have, which year is this? No, let's look for the year in that report. I believe that was 2019. All right, so let's go to exam data. Where is this? Lab procedures. Okay, examination data overview. And so please, you should develop it as a habit to make sure that you read the documentation every single time before you proceed. And understandably, for a surveillance system like ENHANCE, it could be complex, right? But if you're really serious about career in analytics, I would just encourage you to really master ENHANCE. ENHANCE is such a gold mine, and there's just so much in ENHANCE that people are just so scared of and just don't touch it all. For example, periodontal disease, it's a very, very important, outcome, obviously, but the complexity of it makes it, people very unwilling to touch it, right? So you can definitely practice with it and really, really just become very expert in using it. So moral of the story, always come to the documentation and read it, right? So that you're not making any assumptions. All right, now let's go to our data set and just show you how to use that particular functionality to summarize data across individuals. So here we'll come to, let me pick the data set that has enhance. I believe I have enhance somewhere here. All right, good. So here I'll come to data processing and I'll come to arithmetic transformations. So arithmetic transformations has to do with anything that we're dealing with, summarizing things across, multiple variables, whether we are adding or subtracting or summarizing or whatever the case might be. And we click there. And here you have the operations under this. Here, the first one is divide, minus, times, or plus operations between a variable and a constant. That's the example where we wanted to, for example, take the weight variable and divide it by 2 in the case where we were trying to append data sets. So here we have one variable here and we're trying to divide it by a constant. So here the 2 is a constant number. It's not a variable, it's a constant. So that's what we mean by operations that involve a variable and a constant. The next one here is operations among variables. So here, for example, if we're trying to generate a variable that's a sum of, let's say, variable 1 and variable 2 and variable 3, we will use that. But that's not what we're interested in now, really. What we're interested in now is statistical summary across variables, because we want to take the data for tooth number 1 and then generate a summary and then do the same thing for the other ones. So I'm going to select that. Next, it says we should select the variables we wish to transform. And here we can select variables by typing their names. For example, I can type the variable names that I want. So here I have variables. This variable represents oral health module for tooth number 3, the loss of attachment, right? And so I have that. So you can search for variables by either typing here, or you can click on the funnel and switch to pattern filtering, where you want to search by patterns. So let's say I wish to search for tooth number 02, and I'm interested in loss of attachments. So here I have all the measurements that were performed on tooth number 2 pulled up automatically. Now I can select them, done selecting, and then I select, do I want the maximum of all of them? Do I want the minimum? Do I want the mean? Do I want the median? Now, in this case, we said in public health in general, or in medicine in general, we look for the worst outcome when we're trying to summarize health indicators. So in this case, there are 4 measurements on the tooth. There are 6 measurements, but of those 6 measurements, the case definition says interproximal sites. So which means, sorry, I'm not trying to turn you guys into dentists, but interproximal sites are the sites that are adjacent to the tooth. So 4 and 1 are adjacent to this tooth, and 6 and 3 are adjacent to this tooth. 5 and 2 are not adjacent to any tooth, so they are not interproximal sites, right? Moral of the story, whenever you read case definitions, you want to be very, very careful to see what is being said, right? Because so when it says 2 or more interproximal, you can't just ignore that word, right? Of course, you may have little interest in this particular topic, but the moral of the story I'm trying to emphasize is that every single word in the case definition matters, right? You can't just ignore words and say, oh, well, I didn't know that it was interproximal sites. I thought there were 6 sites, so I had to use all of the 6 sites. No, the case definition explicitly said interproximal. So in other words, the sites, and so of those 6 sites that were measured, only 4 of them are interproximal. And we wish to find the maximum. Now, This button here says set a particular value to missing. In Enhance, one of the things they do is if a particular site was not accessed, they put a value of, for example, 99 in that site, right? Now, obviously, you want to make a distinction between 99 and the actual values, because the actual values range from 0 and 20. It should be clear that if you don't make that distinction, all the maximum will return as 99. So depends on your use case, you should be able to know how to, plot which particular value. The old school ways of doing this was when we you used to write code for Enhance, you have to have a separate data processing step where you take all 336 variables and you set all the 99 to missing first. And then you proceed with your analysis. This completely eliminates all those data processing steps so that you can do every single thing in one seamless flow. So this is in case you have such a value that you want to set to missing as part of the operation. So you set, in this case, 99. The next one is assign as missing to rows with any missing value, right? And here, this is the option for you to determine how you want missing values to be handled. So remember we said, do you want the all or none framework, or do you want, if there's at least one information, it should be used? If you want the latter, that if there's at least one information, just use what you have to leave this box unchecked. And then you provide the name of a variable. In this case, I'm going to call it maximum loss of attachments on 202, right? I obviously want to give a name that is very intuitive so that I can remember. And once I do that, I can then click on transform, and the variable is created. So now I have this variable that is a summary of all those sites that I measured for tooth number 2. And it summarizes the information and gives me the worst site for that tooth, right? It looks pretty simple, but try doing that with code with such a massive scale of variables, and then you see how complicated life becomes. The operations on the platform also allow you to do them in batch mode, so that you don't have to be doing for each, in this case, each individual tooth. Of course, your use case might be different, but the rules are the same in every single case. All right, so that's how you summarize data across variables. And whether you want to return a maximum or a minimum, the same will apply. Now, let's go on to the next form of transformation, which is handling of missing values, which is also a form of transformation. It's a form of transformation because it obviously affects the structure of a variable. It affects the inferences that can be drawn from the variable and every single thing. So let's talk about missing values. I always ask this question as a quiz, like, what is the most infectious thing in the world? Well, the answer is missing values. Missing values are the most infectious thing in the world because anything that missing values touch turns to missing. So 1 plus NA is NA, 1 minus NA is NA, 1 divided by NA is NA. In fact, any operation that has to do with NA immediately turns into NA, right? So if you have a column that has missing value, if you were to take the mean of that column, remember that NA is the most infectious thing in the world. You will always return a value of NA for every operation in the world that involves at least one missing value. So the question is, how do we handle that in software? So any software you're using, what it does is that if you are trying to find the mean, it will remove the missing value out of that column. Because if it doesn't do that, all the operations will always return NA because NA is the most infectious thing in the world, right? So that is why the handling of missing values becomes something very important, because how do we do processes? How do we analyze data if we have missing values? Now, let's look at the implication of missing data and the implications of how we correct for missing values. We talked about this figure yesterday in terms of inclusion and exclusion criteria. But let's say that this is your data set here. Missing values means that even though those individuals are in the data set, they have actually left the data set for that particular analysis you're doing. Remember that we said for any procedure you're doing, individuals with missing values are being thrown away. So it doesn't matter that you can see the rows, right? Practically, where it matters, they are not being included. They are being excluded from the analysis. So the question then becomes, are those individuals who have been kicked out because they have missing values systematically different from those who are analyzed? Because I have one data set and I can partition the data set into two, those with missing information and those without missing information. The question is, are those two groups the same? Are they similar? Or are there structural differences between them? If they are different, then we have a problem because it means that we have a problem of generalizability. Here's the cycle of inference that we always talk about. We have target population that gives us the sample population, right? So the sample population, could think of it as your data set. You have a data set of 5,000 people. But when you run a regression, the actual analyzed population is not those 5,000 people. It's the people who are remaining that have information for all the variables, not just one. You must have information for all variables to be included in, for example, a regression, right? So there are 5,000 individuals in your data set, which is the sample population, but your analyzed population is maybe 2,000 people. The question then is, are those 2,000 people representative of the 5,000 individuals in the data sets? Because remember that the target population gives us the sample population. The sample population is what we then analyze, either all of it or a subset of it. And the analyzed population then gives us estimates to return back to give inferences to the target population. And therein lies the challenge with how we handle missing values, right? Because it creates a problem of generalizability for our results. Now, the way we handle missing values depends on how the values were missing, right? So for those of you who have attended our lectures on missing values, you're familiar with this story. But for those of you who are new, I'm going to tell you the story again. A man went missing in his community. And the cops, obviously, the cops suspected everybody. The first rule of law enforcement is that you suspect everybody, starting from the spouse, right? The spouse is always the first suspect. Then, of course, apart from the spouse, you're also suspecting the neighbors. You start asking, oh, did this guy have a disagreement with anybody on the street? Put a reward out there for any information that could lead to the apprehension of the suspect or that could lead to this individual being found, right? So here, they also suspect the man himself. That's the kicker here, right? Because in law enforcement, you can't trust everybody. Love all, trust none. That's the motto, right? So the first suspect is this man. Then, of course, we suspect his spouse. We suspect his neighbors as well. Now, there are two sides to this story. On the one side, we have the guy who is missing, who is also our primary suspect. On the other side, we have the line of suspects, his spouse, the neighbors, and everybody, right? And so the question now is, are these individuals implicated, right? Now, we will have loved to ask this guy whether he's implicated in the story, in his disappearance, but we can't talk to him because he's missing, right? So keep this in mind. This is the framework of a story with which we're going to understand everything about missingness, right? So remember, the guy is missing, and we have two sides of a story. We have two lineups of suspects. On the one hand, the guy is suspect number one, right? We always suspect this guy first. Because think of it, times are hard, right? It's not unheard of for people to fake their disappearance so that they collect the ransom, or maybe they have some whatever plan they have, or some, what do you call all these financial structures, so that, you know, they will then get the money. So it's appropriate to, it's not out of this world to suspect the guy for faking his appearance, right? So that's the story. That's the backstage to the story. Now, here are the rules of engagement. For each of those two sides, if we can rule out that they are not implicated, then we'll say it's random. So in other words, if the guy is not involved in his disappearance, we say that it is random for him. If the neighbors are not involved, it's also random for them. So, but if any party is involved, then obviously it's not random, right? They planned it, they orchestrated it, they executed it. So random if you're not involved, not random if you're involved. All right, so scenario number one. Scenario number one, we found out that after a lot of investigation that it's not very likely that this guy will have faked his disappearance. There's no reason why he will have faked it. He was doing so well. He had a happy family. He had a very great job. He was loved by everybody. Like, why would he fake his disappearance? I mean, we can't rule out for sure, right? We can't 100% say that he didn't fake it. But from all the evidence we've gathered, it's more obvious, or it's more likely than not that we don't believe that he could have done this. There was no reason for him to do that, right? So in this case, we conclude on this side that it's random. And then the neighbors too, the lineup is the spouse and the neighbors. We also have concluded after a lot of interrogation that these guys, they didn't do it. We've subjected all of them to lie detectors, and they are all clean. So it's random here, it's random here, right? In this case, since you have two randoms, we say that data are missing completely at random, right? So that's what missing completely at random means. It means that the missing observations are not related to, in any case, to the variables in the other data sets. And there's no reason for why that record went missing, right? The nature of the question did not lend itself to missing, right? There are some questions that you're going to ask that people are just going to say, I'm not going to answer this question. You ask questions on sexual orientation, right? The nature of that question itself lends itself for people to skip that question, right? That's what we mean by the question being implicated in its own disappearance. The question is sensitive, or there's just something about that question that makes people not answer it. But in this case, there's no reason that this guy was implicated in his disappearance. There's nothing about that question. The question is as harmless as could be. So we don't think that the question was implicated, and we don't think that the neighbors, the other variables in the data set, were implicated either. And so here we just conclude that the data here are missing completely at random. Now, we can test this with statistics. We can see, for example, if data are missing for age, for example, we can say, let's create a new variable where if you're missing, you have a value of 1. If you're not missing, you have a value of 0. And let's do a chi-square test between this new variable and race and employment. And let's see if the missingness is associated with those other variables. So in a way, we can test it, but we can't test it completely because our data set may only have 10 variables. Well, how do you know that it is not associated with the other variables that were not captured, right? This is why MCAR is not fully testable statistically, right? The fact that you have some information doesn't mean that all is well. And for all you know, this guy may have been implicated anyway, right? So MCAR is, we have completely random for both parts, but again, it's not fully testable. And MCAR are things that happen completely by chance. Let's say you are doing the survey and the server went down, just out of just bad luck. So when the reason for missing data are due to bad luck, and bad luck only, then it's most likely MCAR, right? Server shut down, and for that period, individuals who had answered the survey up to that point had missing values for the rest of the questionnaire. But that was just a one out of million events, right? So that is MCAR. So if the reason for missingness feels like chance played a bigger role, then most likely what you have is MCAR. Now, let's move on to the second scenario. Here you have just one random, right? Remember, when we have random here and random there, we say it's completely at random. Completely means both sides. But when you have just one side that is random and the other side is not random, then you say it's just missing at random. You remove the completely. So instead of it being missing completely at random, it becomes missing at random, right? So in this case, missing at random means that there's no reason, there's nothing about that question that made it to incur missing values. The question is harmless, really, right? It just says in these days, everything is sensitive. I can't come up with a good example. It just says, what's your education, right? Right. It's a very benign question that couldn't have resulted in missingness in of itself, right? But then when we do a chi-square test, we see that variable is associated with, the missingness for that variable is associated with gender and with, So for example, we ask a question for age. What's your age? And we see that there's no reason for anybody to, there's nothing about age that makes people not answer. So there's nothing about this question that implicated itself in the missingness. Age is as benign a question as you can ever create. But then you find out that maybe females are less likely to provide answer about their age than males. So you see that there's an association here between missingness for age by gender, right? In this case, we have concluded on this side, there's nothing about this variable that could have led to it being missing. It's not a sensitive question, it's just benign. But somehow, there's an association between missingness for age and gender. So here you see the neighbors are implicated, the neighboring variables in the data set, right? So here we have missing at random. And again, we can test MAR statistically. How? We create a binary indicator for whether 1 for if you are missing age, 0 if you're not missing age. And then we do a chi-square test, for example, between that indicator and, for example, gender. If we have a significant p-value, well, that suggests that there's an association between missingness for age and gender, right? So MAR is fully testable. It's partially testable. We cannot fully test it because even if all the variables in your data set did not show a significant association, well, the question is, how do you know that the other variables that you did not collect are not related? You can't tell, right? And remember, we always can't rule out fully that this guy is not implicated in his missingness. We can't tell for sure. So in this case, you have MAR, missing at random. And then we have no random at all. It's this side is implicated, that side is implicated, right? This is what we call missing not at random, right? There's no random here, there's no random there. This guy is definitely implicated, right? We know for sure that this guy caused his disappearance, and we know that his neighbors assisted him in disappearing too, right? So you can think of a scenario where there's something about that question that led to it being missing. You have a question like, oh, what's your sexual orientation? That's a very sensitive question. Most people may not answer it, right? Or you have a question about, let's say, a clinical question about, let's say, drug effects. And maybe individuals who took the drug are likely to have had side effects and not be present to answer the next question subsequently. So there's something about that question that leads to individuals not answering it for one reason or the other, right? Or you have a question that is at the end of a questionnaire. Let's say you ask a question that, let's say a question like age. There's nothing inherently sensitive about age, but let's say that age question is question number 200 in your questionnaire. Obviously, many people will not get to question 200. And it's because of the location of a question. Nothing about the question itself, but its placement makes it very easy for it not to be answered. So in this case, the question is implicated in its own disappearance for one reason or the other. And also we see an association between the missingness pattern and other variables. Now, of all the three, MNAR is the one that we cannot test statistically, right? Because there is context that we don't know. Like if you give me a data set, how do I know that that question was number 200? There's no way I'm going to know, right? Or the question simply says, oh, what's your age? Maybe there's in that particular culture, age is a very sensitive question to ask. So the bottom line is that you cannot test for MNAR, statistically, right? You have to rely on subject matter knowledge and context to determine that a missing pattern is MNAR. Now, MNAR is extremely important to us in analysis because once you have MNAR, you cannot use any of the approaches that people commonly use for handling missing values. You cannot use multiple imputation. You cannot use anything. You cannot do row-wise deletion. You cannot use, inverse proportionality weighting. In fact, if you use this approach, you are in a worse situation because you're now introducing bias into the study. That's very important to note because most cases of missing value involve MNAR. That's the reality of the world, right? Most cases of missing values will involve missing not at random. So you have a scenario where you have clear patterns of MNAR, but then you also have where analysts are rushing to say, oh, well, let's just use multiple imputation. It's like, okay, it's clear that you may not have a very solid understanding of the assumptions behind each of these procedures, right? The moral of the story is that don't just rush to say, oh, I want to do multiple imputation, right? Because that could backfire. So in summary, MCA is when we have missing random here and random there. Missing at random is we have random on only one side, but the other side is associated. And MNA is we have not random here and not random there. Again, I cannot emphasize this enough. Beware of quick fixes. I'm on a group where somebody posted this a long time ago. They're like, oh, AI is sure doing well for some of us who are doing modeling. That even Google Colab is now generating codes. It takes me 3 minutes to do data cleaning. This includes checking for missing values, drop NA, fill NA, no stress at all. Just apply it and you're home and dry with data without missing value. No. This is as wrong as could be, right? You can't just say, oh, I'm going to have an imputation where I'm just going to fill all missing values with the mean of that column, or that makes absolutely no sense, right? So we want to be very wary of that. And please be very wary of, there are a million and one, AI platforms that are just telling you, wow, just, it's so easy, right? This one says missing data is a common problem in the world of analytics. And, it says, this can be a simple data imputation. For example, calculating the mean or median value of a column and using it to fill the missing values. As a data analyst or as a researcher, that should just really shock you. You should really not do that. That is really, really bad advice. So the cautionary note is that the road to heaven feels like hell, and the road to hell feels like heaven. When you are just saying, oh, just give me a button. People always ask us, oh, where is the button in chi-squares to just handle missing values? Like, no, it's a bit more complex than that, right? We can't provide you a button to just click and handle missing values because that's not science. That is I'm not even sure what we can call that. And the road to hell is paved with good intentions. The good intentions that, well, I have missing values and I want to correct them. I want to make sure that I have a larger sample size. It's a complex problem. You can't just oversimplify the problem in a way that you will just use one button to fix the problem, right? So the best case scenario is that you want to make sure there's prevention. Prevention is better than cure. No AI, I cannot repeat this enough, no AI can fix your data problem. No single button can just fix your missing value problems, because for you to rule out, you have to first of all rule out that you don't have MNA. That's your first job. Is this missing value a case of missing not at random? That's what you have to first of all ask yourself. If it is, game over. You cannot use any procedure. You just have to accept your fate. You have to go and collect new data or something else, right? But you cannot use any of those techniques because they will cause more problems. So this is words of wisdom. Better to have a small bowl of clean water than a large bowl of contaminated water. It makes no sense for somebody to say, well, I want to have more water, right? So I have a bowl of very perfectly clean water for drinking, but I have this big bowl of contaminated water. But since I want a lot of water, I'm just going to add them together. That makes no sense. That's extremely ridiculous, right? It's better to have small amount of clean water than to say we'll just add together water and just make it voluminous. That makes no sense. So the first rule of thumb is that thou shalt not step from a frying pan into the fire. You're already in the frying pan with missing values. The last thing you want to have is a case where you worsen the scenario. All right. Now, what are the scenarios for handling missing values? Again, remember we said that you have to first of all evaluate the kind of missing value structure you have. And if it's appropriate, then you can then handle it appropriately. So let's look at it in a simple pictorial form. So let's imagine that this is a game of sumo wrestling. And here the rules of the game are a bit interesting. There must be two people to be on the team to fight, right? So you have a team of twos, and you must have two people. So here we have 4 scenarios. Scenario A is that we have 2 guys. We're going to call them Alpha and Bravo. Alpha is the first guy, Bravo is the second one. In the other 3 scenarios, Bravo is missing. So the question is, we want to make sure that we correct the problem, right? The question is, how do we do that? Well, here are some of the common approaches we use. Let's go through all of them and just make sure we understand them. We're looking at two things. What is the impact of each method on validity and precision? But again, remember that the point we're making here is that data analysis of missing values is a form of transformation that has significant impact on validity and precision, right? That's why we cannot take it lightly. That is why we cannot provide a single button that says, oh, just click here. Sounds even ridiculous saying it. Just click here and it will take care of all your missing data problems. That's not how it works. All right, so here we have the three common ways of handling missing values: listwise deletion, multiple imputation, and inverse proportionality weighting. So let's see how they work, right? So let's keep our story. So in this story, after these guys fight, they have to write a letter, handwritten. And when we get the letter they've written, we're looking at two things. We're looking at, is it true? Is what they said true? That's number one, the veracity of the information on the letter. And number two, how is their handwriting? Is the handwriting clear or is it faint? You can imagine that if somebody has finished fighting a very fierce fight the whole day, they're going to be tired, right? So we're trying to see, we're trying to gauge how much of their strength is remaining. So we're interested in, is it true? And is the handwriting legible, right? So keep in mind, those are the two parameters we're looking at. Again, we're trying to see how does this tie in with validity and precision. If it's true, that means it's valid, because validity means truth. If the handwriting is very clear, then it's precise. If the handwriting is not clear, it means it's not precise. So here, we have two guys, they were fighting together. Since they're a team of two, their energy is conserved, and they won the fight. They took first place. So their handwritten note was like, hey, we crushed it together. Two big boys, full strength, right? Is it true? Yes, the message is true. And it's clear, right? The writing is legible. So this is just to say that when we have our full data set, well, of course, assuming that the initial sampling was at random, it means that we're going to have validity and we're going to have precision. The writing will be clear, meaning that the confidence intervals will not be all over the place. It will be narrow and well-defined and very sharp. And it's going to be true too because of the random selection. So here, there's no problem here at all, right? No missingness here. All right, scenario number two. Here, this guy is alone, and the second partner who was supposed to join him, Bravo, did not show up. And the judges said, well, if you can fight alone, we'll just let's fight alone, right? So he fought alone. He lost. And in this case, he wrote a note. He said, I fought hard, but it was just me. I'm so sorry I dishonored you guys by losing. I am famished and finished, right? So here you can see that he took last. He wrote a very truthful message, right? But his handwriting is very illegible. As you can imagine, he's very tired after fighting. So in this case, when we have a data set and we have some individuals who have been lost from that data set, if they were lost in a way that was at random, that's fine. That's, analyzing that data set will always give us validity as long as those individuals were lost at random. So in other words, we're saying, as long as there's no difference between those who were missing and those who were not missing, we don't have anything to worry about. As far as validity is concerned, we will still get results that are valid. We may have results that are imprecise because we have smaller sample size, and so our confidence intervals are going to be wider, but the results are still going to be valid, right? So in this case, we don't have to worry about validity. So here in this case, the message is true, which means it's valid. And the text is, is imprecise because we have fewer people, right? Now let's look at multiple imputation. Now, with multiple imputation, this guy Alpha is alone and he's like, okay, I don't want to fight alone. He looks at the crowd and says, I'm going to select one person that looks like an athlete. And then he picks this guy who is not even into sumo wrestling. He's just, maybe fights, taekwondo or whatever the sport is, right? And he is a really horrible fight. He's not in any way in shape to fight. He is not in any way exchangeable with Bravo, who was lost, right? Now, this guy is, he's in fact in a worse condition than if he had fought alone, right? That's the point I'm trying to make is that having somebody there is not helpful if they are no way exchangeable to what you should have had there. Because now you're in a war situation. This guy's getting your way. He doesn't know the rules. You're getting a lot of red cards. I don't know if there are red cards in sumo, but I'm just making it up, right? So in some instances, yeah, you have been far better if you had been alone than now that you brought this guy. So now, of course, he's Gen Z, and it's like, oh yeah, we crushed it. No, you didn't crush it. So in this case, the writing is full of lies. So of course, it's not valid. Of course, it's going to be precise. Whenever you have more people, results will always be more precise. But that's not precision is not the big end game, right? Right? Is it valid? First of all, is it valid? We ask validity first, and then we ask, is it precise? So here, the guy that you have two people for sure, you have solved the problem of missing values by injecting somebody, but it's made things worse. Here, at least you were one person and you lost, but at least that was valid. Here, you are two people, so you have precise estimates, but you don't have validity. So you're in a worse situation, right? So this is just to exemplify what I was saying earlier, that you need to be very wary of just applying multiple imputation to everything because they require very heroic assumptions. They require that data must be missing at random. So if you have a case of missing not at random and you apply those techniques, you are like this guy. This is exactly what you are. And then lastly, you have a scenario where the guy has miraculous powers and expands himself by so that he's still one person, but he's like two. He has summoned the spirit of the missing guy into him. And again, in this case, he has lost. It's valid. But in this case, his handwriting, as you can see, is very poor. So it's imprecise. Both inverse proportionality weighting and multiple imputation belong in the same category. They require the exact same number of assumptions. They both require that data be missing at random. In both cases, you're going to be in a lot of hot trouble if data are missing not at random and you still use them, right? So the moral of the story is that you have to evaluate first and foremost and rule out that the missingness pattern is not MNAR. That's the first thing you have to do, right? Most people come and say, oh, I won't have missing values. So you ask them, what pattern of missingness do you think you have? They're like, I don't know. Like, okay, then you should not be talking about missing values handling. You have to first of all go and evaluate the kind of missingness you have, first and foremost, and then we can then figure out how to treat it. It's like a doctor saying, oh, you go to the hospital and the doctor has not even spoken to you and say, oh, here's the injection we're going to use. It's like, injection, you've not even spoken to me. You don't know what condition I have. You've not diagnosed me, and yet you want to give me an injection. That's how ridiculous it is when we try to fix missing values without diagnosing the basis or the kind of missing values that we have. So that's why we need to be aware of the assumptions, right? Imputation versus deletion, because again, they assume that data are MAR, missing at random, but most of the time, what we have is MNAR, missing not at random. So this is a report from, even big organizations get this wrong, right? This is a CDC report that looked at imputed state level prevalence of this outcome, diabetes in adults, right? Now, here is the what we want to focus on. They said self-reported diabetes status and other variables might be subject to diagnosis, recall, and social desirability bias. So in other words, they're saying that there may be some factors that resulted in missingness that are outside of the questionnaire. So again, remember, whenever an external factor was what led to missingness for that variable, then you have MNAR. It's that simple, right? If there's something that is an external influence, maybe some social desirability bias, or maybe some, it's a shameful question, external pressures, right? Once it's what is causing the missingness, then what you have is MNAR, period. So here they're saying that, well, recall social disability bias, things of that nature might have caused missing values. But you, at the same time, you just told me you still use multiple imputation, even though the missingness pattern is according to your own judgment, MNOR, right? It's missing not at random. So that means you cannot use multiple imputations, period. So we want to understand these assumptions in and out and use them. And again, if data is corrupted, remember that with multiple imputation, you're using the available data to predict and generate values for the missing ones. If you have already said the reports are trash, then you have garbage in, garbage out, right? So what I'm just trying to emphasize is that we don't want to think of those solutions as a magic bullet. That there's something called multiple imputation, we just apply and boom, it solves our problem. No. Far from it. It's not a magic solution. We want to be very intentional. We are researchers and scientists, and want to think about these things very carefully. Now, lastly, numeric transformation. This is the one that most people understand as transformation. So let's just quickly run through it. So in general, most of the methods we use in regression, again, that are based on assumptions, right? We assume, for example, that there's normal distribution, that the distribution is normal for linear regression. But sometimes it's not true, right? It might be skewed, but it's a screw. It might be skewed in one direction or the other. It might be left skew or right skew, right? So the assumption is violated. Now, let's talk about distribution so that we understand what we're saying very clearly. All distributions have a body and a tail, right? Think of this dog. This is the body of a dog. This is the tail of a dog. The same thing applies to distribution. You have the body and you have a tail. It's the exact same thing, right? The body is where most of the data lies, right? But think of a dog that had a very, very long tail. It's not hard to imagine how it's the tail that controls the dog. Never mind that most of the data is in the body. The tail calls the shots. Imagine a dog that had a very, very extremely long tail. Imagine how frustrating life would be for that dog. The dog is just going around, and the tail is circling around the pole, and it can't move further. And the tail is absolutely calling the shots, right? So maybe the way to free this dog and make him a normal dog is chop up that tail, or at least chop up part of that tail. Then the dog is now normal, a normal dog again, right? The exact same thing happens to data. The guys in the tail, they are not as many as the ones in the body of the data, but they call the shots. They cause a lot of problems for the data. And the question is, if the data requires normality, how then do we make sure that we get to that point? How do we transform the data to that point? Well, we can find a way of chopping the tail. Well, not literally. We don't just chop off the tail to make the dog normal, right? The same thing with our distribution. We find a way of correcting it. So it's like a photographer. The photographer follows some rules set by their father or grandfather. The rule says that you cannot go into a trashy house to take pictures. If you're going to take a picture of a house, it must be neat and stable. Because your life is too valuable for you to go to a house that is sketchy. So you definitely cannot go to a house like this, but you can go to a house like this that is fine and nice, and So that's the same rules that regressions follow, right? The regression rules were set by their forefather, in this case, linear regression. Linear regression is like the grandfather that sets the rules for regression. So in this case, if the house is not correct, if the house is in a state like this, we can't take pictures of it. We have to correct it, right? And there are so many ways of correcting it. We can take log and square roots, or cube and square, Now, we'll in a minute talk about how to know what to take, right? But it should be very also obvious in this picture that if you want to try and solve a problem, you solve it from the part that is defective, right? If the house is sinking on this side, if this side is the one that is sinking, well, that means that's the part we have to lift up to level the house. That's the exact same thing we do with transformations. So most people find it very confusing that all these transformations, geez, how am I supposed to know which one to apply? Well, once you understand the principle no longer sound like French or Latin or Spanish to your ears, because you understand that our goal is to chop off the tail and make things more normal, right? So that's the goal in a very simple manner. We're not going to complicate this. So let's first of all understand what these terms are, some of these terms. Everybody talks about log, so let's understand what a log is. A log is a way of making something smaller. So we were taking classes on geography in our secondary school or high school. And if we're studying about the earth, it would be nice to have the earth in the classroom. But obviously the earth is too big to put in the classroom. So what do? We take the log of the earth and put it in the classroom. So a globe is like the log of the earth. It's like a compressed version of the earth, right? That's what logs are. They're a compressed version of something, right? So when we say log to the base 2 of 8, we mean like, what number do we have to raise by itself, raised by this base to give us this number, right? So in this case, the answer is 3. So now let's come to how this works or why we're trying to take the log, right? Remember that we have a distribution that has a long tail, like the dog with this long tail, and that tail is causing a problem for this dog. Our goal is to chop off the tail so that the dog can move freely. Dog can become a normal dog. It's not a dog with that kind of a long tail is obviously not normal. It has a lot of problems. So how do we address this? So let's look at, for example, a hypothetical example of a distribution that is right-tailed. And let's say this is income distribution. I am here and my income is $10. Elon Musk is here, his income is $100. The goal is to make Elon Musk less extreme. In other words, we want to chop off his tail. Imagine if there was no tail, this will be almost normal here, right? So how do the goal is, the question we need to ask ourselves is, when we look at a distribution like that, what ways can we use to pull the tail a little more to the body? That's what we're trying to do. So it's not complicated. Think of it that you have a tail this side or that side. Your job is just to pull that tail to come towards the body. So what could we do? Now, could we use a power transformation? Like, could we square this? Well, if we take a square of 10 squared will be, 100. 100 squared will be a much bigger number. No, that will not make sense. It will even extend the tail more. Our goal is not to extend the tail even more. It's to pull it inwards, right? So in this case, we can think of, how about we took the log, right? Imagine you have a log cabin. The house is exactly the same, right? But the guy who is already small doesn't have to bend so much to enter into this log cabin. The giant has to bend a lot more to get into the exact same cabin, right? That's what a log transformation is doing. It's saying, well, we're going to reduce all of you. All of you, your height is going to be reduced when you're entering the cabin. You have to bend. But the guy who is bigger has to bend a lot more to enter the same cabin, right? That's what log transformations do. They say already, we can see this distribution is there's a very long tail. We want to pull this tail so that it's less extreme. So we're going to apply a log transformation to everybody. It's not just applied to, Elon Musk. It's applied to all of us. But just by the nature of log transformation, as it's compressing values, the bigger guy gets compressed a lot more. He has to bend a lot more to enter the log cabin, than the guy who is small, And that's exactly what it does. It now pulls the tail back towards the body, right? So in the case of log transformation, we can only use it when we have, for example, values that are positive and values that are non-negative, right? And that should be immediately obvious to us. We all have calculators, you can try that to see why that makes sense. If you take the log of 0, that always results in an invalid input, right? Because that makes no sense. The same thing with a negative value. Let's see, how do I make this negative? Okay, good, right here. So that always results in an infinity, right? Or values that are that are not mathematically, comprehensible. That's why a variable that you are trying to apply a log must be, non-negative and must not have zeros. Sometimes some researchers try to address that problem of if they have a lot of zeros by adding some small values to everything, but you're already altering the data set already. It's like you came to take a picture of a house, but instead of just taking the picture, now you're painting the house and you are altering. It's not longer the same house, right? So that's why there have to be some restrictions on when it makes sense to use a log transformation, for example, and when not to use it. If you notice on your calculator, there are two types of log expressions on any calculator you use. There's ln and log. This is the natural log. In Latin, it's logarithmus naturalis. That's why it's ln. And then you have common log, which is log to base 10, right? When we say log transformations, without saying anything, in general, we're referring to the natural log. So you need to be aware of that. The log to base 10 is just the general common log we use. It's called a common log because commonly we count in base 10s. There's a reason why we all have 10 fingers and 10 toes, because naturally nature is primed such that we count in tens, right? So just the common log is called common because it commonly uses base 10 in its calculation. The natural log is it doesn't use base 10, it uses base 2.718, which corresponds to, it's called natural because it corresponds to natural growth or decay process. If you have an infectious disease outbreak or you have some animals and it comes, every unit time you see there's almost doubling of the number you have, right? So growth or decays in nature in general doubles, and so that's why the natural log is set to 2.718 as the base. But the moral of the story here is that when we say log transformation and we don't explain, we're referring to the natural log. And it should be obvious to you why we're doing natural log transformations, which is because we have a right tail distribution. Again, log transformation only applies to a right tail distribution that does not have zeros and does not have negative values, right? Now let's see how we can implement that on the chi-square platform. So we'll come to data processing. I will come to numeric transformations. We can select the variable we want to transform. Let's say we're interested in, let me go back to our data set for today. So data processing will come to numeric transformations, because that's numbers. We'll select the variable we want. Let's say we're interested in I think we had a glucose variable. Oh, did I overwrite this data set? Oh, sorry. This is the Let's use this. Let me just upload the data set again. Let me replace this. I want to use the same data set that you are also using. Where did I keep this data set? Let me just upload from. I have completely forgotten even the data set that is a case study. You know what? I think day one had the data sets. I'm just going to use day one's data set because that's what we're using now. All right, so numeric transformations. I'm going to select a variable, for example, total protein, for example. The platform automatically filters out variables that are not eligible. And then you can select the specific transformation that you want. Log transformation, natural transformation, reciprocal transformation. So your homework is you should really sit down and think. If I have a long tail to the left, what procedures does it make sense that will not, because the goal is to apply a procedure that applies to everybody, but that affects the people in the tail more. And The goal is to pull them towards the body, right? Not to make it, we're not trying to make the tail of a dog even longer. We're trying to make the tail shorter by pulling it to the body, right? So you should think of, okay, if I apply this procedure to everybody, is it likely to make the tail longer or shorter? So you don't have to memorize transformations, nor should you just imagine. So for some people, they imagine that, oh, every single problem in the world is log transformation. No. Right? So we want to think from first principles. If I took the square, will it make the values bigger in the tail? Will the difference even be bigger, or will the difference be smaller? That's what we're trying to achieve here, really, right? So here, we'll take total protein. If we're trying to do natural log transformation, then we'll select this. Again, remember, log transformation, you can always customize your base. If it's a common log, that's log to base 10. Well, but like I said, when we just say log transformation and we don't provide any additional details, we mean the natural log. So I select this and I provide the name. And in this case, I'm going to call this, for example, protein log, right? Log of protein, and let's transform. So that's transformed. Now let's look at the data set and let's compare the values for those two variables. So let's preview our data set and let's compare the values for let's see, protein. So let's look at the observations here. We can see that the range of values for this is from 4.7 to 10.2. Those are the range of values. For the naturally transformed log, let's look at the values. So you can see that the values here are quite less extreme, right? Which is essentially what the natural log does. But you should be aware that once you apply a transformation like that, the meaning changes, which is a very, very important thing we need to emphasize. How we interpret the results change automatically. Now, if you're using the chi-square platform to do your analysis, you don't have to worry about the interpretation because the platform will interpret it for you. And the platform is an interpreted platform, which means that it's not just doing the analysis, it's also interpreting the results based on what has been captured. So for example, let's say that we did a linear regression. Let's look at a quick example. If we did a linear regression here, let's come to estimate and come to regression analysis, linear regression. And let's say we selected the protein, the log transform protein. Note that there is no additional checkbox here. When you select a variable for analysis, what the platform does is that it automatically runs a set of diagnostic tests in the background to see whether or not that variable is skewed, whether or not it requires transformation, and the platform will show you the options that make sense for that variable for it to be transformed so that it meets the assumptions for the analysis. So for example, in this case, protein log has already been treated and it's nice. But if I, for example, selected, let's say protein, the original one. So now you see a checkbox that says enable log transformation. Why is this so? Well, the platform has run a series of diagnostics in the seconds I selected it, and it has seen that, well, this variable is right-tailed, that this variable is skewed, obviously, and that there are no other contraindications to not using it. There are no zero values, there are no negative values, and that the best way of transforming the data will be a log transformation. So if I want to transform the data, in this case, I just click on enable log transformation. So whenever I see that checkbox, it means that all is not well in terms of the regression you selected, right? So in this case, I select enable log transformation, and the question is the variable already log transformed? So the option here is yes or no. No, so I will select this option that says no. Apply log transformation to my untransformed data. So I don't want to go and transform the variable myself and then bring it back. That's a lot of extra steps. Like, why can't the platform just transform the data for me, right? Because I don't even want to go and make a mistake and do, one other log when I meant the other type.
So in this case, when you select a variable that is obviously skewed, the platform will ask you, all right, it is not normally distributed. Do you want to transform it? It was to display the appropriate type of transformation that makes sense in your case. And your job is to say yes or no. No, the variable is not yet transformed. So I'll select that. So let me select a few predictors like race and let's say smoking status, for example. The platform selects the reference group, and I'm going to now estimate that. All right. So notice that the presentation and interpretation of results for when results are transformed is quite different from when it is not transformed. So when it's just nominal. So here the platform presents coefficients, but it also presents the results in percentage changes, right? In the interpretation of the results as well, when it writes out the results, everything is done in the way that it ought to be done, right? So you see, all the results are reported percentage change. Because when you do, for example, a log transformation, you can no longer interpret the results in terms of differences in means. That is, we have left that stage a long time ago, right? Any interpretation in that way is incorrect, right? So it's not just about doing the transformation, it's also interpreting the results accurately in a way that is intuitive. So the platform writes all of those things for you. So here you can see all the results are expressed in terms of percentage change, right? So here you also have some context here. So here it says the coefficient in this log model have been modified to present effects as percentage change points. The value can be derived by exponentiating the coefficients, subtracting 1, and then scaling the results by 100. For example, a coefficient of 0.618 for a continuous predictor means that the mean value of the outcome increases by 18.29% for every unit increase in the predictor variable, right? So that you have context for the results being interpreted, right? So that's why here you have in the table, you have the results presented for the coefficients, but also the percentage change expressed from the coefficients, right? And if you want to get this, again, you take the value here, you take the exponent, you exponentiate it. So in other words, 2.718 to the power of this variable, you subtract 1 from it, and then you multiply by 100, right? That's how you derive the percentage changes from the coefficients. But I cannot emphasize enough that once you have transformed the results, you can no longer interpret them as though they were not transformed. That is completely incorrect. Now, let's compare these results to how they would sound if we had not transformed. So let's go back here and we'll uncheck this. We're going to interpret the results just raw, right? So let's estimate the results now. All right, so here, now first of all, you no longer have that column that shows results in percentage changes, right? You just have coefficients. And that's how the results are going to be interpreted. The coefficients now mean differences in means. If you look at how the results are plotted, you also have regression coefficients, not percentage changes, as we had before. If you look at the text, you have results presented as betas now, which are regression coefficients, and no longer as percentage changes, right? For every single transformation, again, that completely alters the structure of the variable, but also how we interpret the results, right? So that's something I cannot emphasize enough. That's one of the most, the greatest blunders you see in peer-reviewed literature where people transform variables, but they do not understand that that has complete changes on how you interpret the results, how you present the results, and every single thing that you do, right? So half knowledge is dangerous, so we want to make sure that we understand completely that transformations have significant impact on how the results are interpreted and presented as well. All right, so I think yeah, I think that's the end of a lecture. I'll stop here and take questions that folks might have.
Thank you very much, Prof. Do we have questions? Temi?
Okay. Hi, Prof. Thanks for the very detailed explanations. My question is a very simple one, and it's basically how you get to the button that, facilitates the append and what's the other function? Append and
Merge.
merge functions. Yes.
We come to data processing. So the
Yes,
way
I got that.
Very good. The way it's organized is that under data processing, the first set of actions are basic
Yes,
derivatives.
and transform. It's very good. I've played through, the site and it's very helpful.
Okay.
But I just had a bit of a confusion because definitely it's in the middle, right? It's under transformations.
Yes, exactly. So it's under, come to the data processing, then you come to the data set actions.
Oh, right. Okay.
And then you come to combine data sets.
Yeah.
And then you have append and merge.
Ah, good. Okay. Thank you very much. Appreciate it.
Sure, yes.
Betty?
Hello.
Betty, please, sorry, it's Betty. Betty.
No, it's
All right. We can't hear you, Betty, so I'll give the other person a chance. Can unmute yourself. Can't pronounce your name.
yeah. Thank you very much, Israel. It is Iris Regan from DSC. Just want to ask if this lab will be able to share with us, because I was on late today. Can we have the slides?
The slides we provided. Lungle can comment on further on that.
Thank you.
Yeah, we'll share them on our LinkedIn page. Just check tomorrow. You'll find them there and you can download them. Chi-Square's page. Thanks. Prof, what is the difference between this program and SPSS and the kind of advantage of this program?
By program, well, so I assume you mean the software. Well, the Chi-Square platform is a one-stop shop for research. So it's not just for analysis. You can do your analysis. You can, so for example, the analysis we're running, we can decide to write our manuscripts. Which one was I running now? Yeah, but you can write the manuscript, you can do analysis, you can collect survey on it. But ultimately, I think the bottom line is what the crux of the matter is. What are your needs and what are you comfortable with? But the Chi-Square platforms focus is much broader. Question is, how do we provide an environment for the full scope of the research process, from data collection to analysis to manuscript writing and everything in between. So just different focus areas. All right, next question, please.
Thank you. Thank you, Prof. Please, how do I get more understanding on this teaching? I really want to know data processing and analysis. Thank you.
So the first step is attending the lecture, but it's impossible, obviously, to know everything from attending the lecture. The lecture is the easy part. So there should be zero expectation that somehow from the lecture you will understand everything. The lecture is just supposed to point you in the right direction. Then from there, your job is to learn and practice and practice and practice, right? It's best to practice with a benchmark. So you take, for example, a report like this and say, okay, I want to reproduce this report by myself. I need to make sure that I get the exact estimates in this report as when I run my own analysis, right? If I can do that, that means that I am confident that at least I'm doing the right thing. And then you do that, that's going to, the first one is going to take you a lot of time, and that's good because you cannot learn without making mistakes. And then subsequently, you can then spread your wings and take on bigger projects. But yes, you will have to put in hundreds of hours into your own craft, and that's how you're going to become very good at this. So it's not just the lectures. The lectures are small, very tiny little part of it. The rest of the work is going to be in the dark, in the shadows, where you're just alone and practicing and making mistakes and starting all over again.
Thank you, Prof. Bismarck?
All right. Thank you very much, Prof. I have two questions. My first question has to do with the manuscript aspect. I'm sorry, yesterday I left early. That was 25 minutes before you closed, so I don't know whether you touched on that. Sorry, forgive me. But the manuscript aspect, when you finish everything, is there a space on the software where you export and so to Word so that you get everything at Word? That is the first question.
Okay. And the second one?
And the second one has to do with, SPSS and, no, Stata, I can speak for Stata. Stata allows you to export, you can export data from Stata to SPSS if I'm not mistaken. But so does this platform allow you to export data from, import data from other software like Stata and SPSS apart from SL?
Yeah, you can import data from any formats. And
all right.
So that's not a problem. And yes, and here, if you have a manuscript, you can download as a Word document or PDF.
Okay. All right. Thank you very much.
You're welcome. And tomorrow we're going to focus on, tomorrow's session was going to be on a very, very, very important kind of transformation, which is analysis of weighted data. If you cannot be in public health and not know how, and not be an expert in analyzing complex survey data, I will mean data like this, where you see something like, like clustered sampling, right? Here you see NYT is the cross-sectional, voluntary, school-based. Oh, so many descriptives. So in this case, you'd have to account for the complex design, right? So here you see, for example, they say data were weighted to account for the complex survey design and adjust for non-response. That one line summarizes what complex survey data is. You could literally write a manuscript every week if you wanted to, because there's so much data in the world. Like there's so much. So when people complain, oh my gosh, I don't have data, or when people say, oh, I'm afraid to give people my data because they're going to steal it. I'm like, dude, there's so much data in the world. Like, why would anyone want to steal your public health data, right? But first and foremost, you have to first of all learn how to analyze complex data, and that's what we're going to be covering tomorrow. So tomorrow's session will be a case study that will take a report and generate a research question and generate a manuscript from the beginning to the very end, in line with all the things we covered from day one to today. Thinking of how do we formulate the question, how do we select variables, and we're going to do that very slowly and intentionally from beginning to the very end. All right, next question, please.
Does the Chi-Squares platform perform machine learning techniques?
No.
As sophisticated as Chi-Squares is, affordability is my issue. Do you have any soft packages for individual early career scholars under the sorry state of national remuneration?
Yeah, Lungile is working on that. You should be answering those questions yourself, Lungile.
Okay. Do we have any other questions I did not answer? Someone was asking about the transformation. Why did you transform the data, the variable? Let me see. Is that question? Betty, can you please post that question again?
But we transform the data because it's like, oh, the party says the rules of a party says you must dress in white, and then you come in dressed in black. Well, you have to change that shirt. You have to transform your shirt to white to meet the requirement for the party. So if the party says, if the analysis says that regression requires that the data be normally distributed, and here you come wearing a not normal distribution or wearing a right tail distribution, well, you have not met the requirements for the party, and so you have to be transformed to meet the requirements. At least if you want to use that regression. If you want to attend this party, you have to be dressed in white. That's why we transform to meet the requirements for certain analysis. All analysis have assumptions. And when those assumptions are violated, we might have to transform. When you're using the chi-square platform analysis suggester, so when you're using the analysis suggester, let's go back to analysis, day one or whatever. For whatever suggestion, the platform, so you don't have to worry. The good thing about the chi-square platform is that you don't have to worry your head about these assumptions, right? Oh, is it distributed, normally distributed? Is it right skewed or left skewed? No. The platform does all of these checks for you in real time. So if any of those assumptions are violated, the platform will tell you, well, in this case, these assumptions are violated, and here is how to fix it. And all you have to do is click a button, really. But again, that is the theoretical basis for what's going on, because analysis requires certain assumptions, or certain analysis requires certain assumptions, and when they are not met, then we have to correct for them.
Thank you. My question is, how can I collect daily data and do analysis at the same time, draft a monthly report at work using the chi-squares platform? How?
Well, you can set up data collection. That answers part of your how do I collect data? And so once you set up a data, you can generate reports. The platform allows you to generate reports automatically, so you don't have to be generating a report every day. So the report will give you an update. So you can download it every day, every hour if you wanted. So that's how you can do it.
Okay. I beg that you repeat what you just said. If you transform the data, which is income, you can no longer use the tests on that variable? Question mark.
If you transform a variable, it means that at that point, it's no longer the old guy, right, that it used to be. It's now a new guy, new rules. That's the point here, right? So the way we interpret the results and everything changes at that point. So that's what we're saying. So transformation is not just a free gift. It comes with, with some requirements attached to it. And so to transform it, the way you interpret it is different. And that's why we have to be very, very careful on how to interpret those results when you have transformed the data, because it's no longer the same as though the data were untransformed.
Okay. I think that's it. Thank you so much. Thank you, Prof.
Okay.
We appreciate it. Yeah, no more questions, right, everyone? Yeah, thank you very much, Prof.
All right. Thanks, everyone. Have a great day.
And thanks, everyone.
All right, cheers.
Okay. So thanks, everyone. We are working on a model to make the platform extremely affordable for everyone. So you can just be on the lookout. In the next few weeks, we'll share the details. Those who are asking for recordings, just check out our YouTube channel. Our recordings become available as soon as we start the session. So Every session from day one is available on YouTube, including this one. I'm going to share the link now for the person who asked for it, but at any day, anytime, just check out our YouTube channel.